So good morning, everyone, and welcome to Manitoba Ag Days this fine Thursday morning in January. My name again is Edgar Hammermeister, and I am the lead agronomist for Western Ag Professional Agronomy with responsibilities in Southeast Saskatchewan and Manitoba. Before I get into my presentation this morning, a little bit of a background on myself. Along with, I've been a consultant for Western Ag for going on 26 years now. Working primarily in Southeast Saskatchewan. And I also manage a farm there near the town of Alameda. We manage about 4,300 seeded acres now. Now, before the presentation, just a couple of questions or a few questions for the audience. First, who in the room buys and applies fertilizer? Well, I do as a farmer. And who in the audience sells or recommends fertilizer? Well, I recommend fertilizer as an agronomist. And who in the audience is looking for return on investment on that fertilizer? Well, we really should all be looking for return on investment on that fertilizer. But as much as our city cousins think that farming is a lifestyle, we know that ultimately it is a business, and it needs to be an economically viable business. And as we assess our businesses, we're looking at return on investment on inputs, on equipment, and increasingly return on investment on logistics. Because we're getting more and more pressures to grow yield, to grow bushels. Our cost of inputs are going up, the cost of equipment is going up, not to mention the increasing land rent or the cost of land ownership. There's all kinds of pressures for us to be maximizing our yield on the farm. But there may be no greater pressure to maximize yield on us than coffee row. But to maximize yield is not necessarily maximizing benefits. And that's what I'm going to drill into a little bit in this presentation. So let's talk about maximums. What is currently possible? Well, I decided to take a look at the Guinness Book of World Records and found out that Tim Lamyman, he set not one, but 2 world records in 2022. He broke the wheat and barley yield records. Now I'm going to focus on the wheat yield. What was the variety that Tim grew? What was DSV champion? And he grew 267 bushel an acre wheat. Incredible yield. Now a little bit about that wheat. Well, it was a winter wheat, and it's a feed wheat, and for its quality, and it's typical for a feed wheat. Protein is lower, and the falling number is a little bit lower than the varieties that we typically grow in our area. The agronomy package around that record-setting wheat, well, it was seeded on September 24th at 134 pounds per acre. There were 3 nitrogen applications made for a little over 90 pounds each. For fungicides, herbicides used, there were a total of 10 different products used to protect the yield potential in that crop. And in the description of the agronomy, there are a couple of biological products used. Now, more details in the agronomy package, it was indicated that the crop had tillered, and I was amazed at this, 600 to 650 heads per meter squared by February. By February. So obviously this isn't in our area. Where did this record-setting wheat get grown? Well, it was in Louth, Lincolnshire, which is on the east coast of England. And the type of soil that Tim is common in the area is the Holderness Association. It's a loam to clay loam soil with a pH of 7 to 8 and a clay content of 25 to 30%. So what kind of growing season does Tim experience there in Louth? Well, it doesn't get very cold there. Actually, it doesn't get very hot either. It's a very mild climate, being so close to the ocean. It doesn't even freeze there in Louth. But the growing degree accumulation is pretty slow as we go through December, January, and into February. Now, for rain from the seeding date to the harvest date, over those about 10 months of what's influencing yield potential, there's about 24 inches of annual rain. And now they did say in the write-up that the 2022 growing season was a little bit drier than normal. I think all things considered, that probably helped the crop with its yield, because there would have been a little bit more sunshine and a little bit less disease pressure. Now, 24 inches of annual rain spread out the way it is over the growing season, well, that's a lot different than what we have here on the prairies. And I just grabbed some information from Brandon from the Environment Canada data. And for our 100-day crops, we don't have a very long growing season. Really, May, June, July, that's really what's setting up our yield potential. For corn and soybeans, we would be looking at August and a little bit of September. Now, for our 100-day crops, May, June, July, the 30-year average rain received is about 8 inches. But for Tim growing 267 bushel wheat and all the rain that he receives, when we compare bushels per inch of rain received and considering our growing conditions, I think here in the prairies, we're doing a pretty good job growing the bushels that we do. But as I described to you, the conditions, the circumstances that Tim was growing his wet record-setting crop, you were comparing the soil characteristics, the growing season scenarios. I imagine that you were thinking about that, and in essence, you're really putting to work the mental model you have of growing crops on your land relative to that in England. So let's drill into that a little bit more. And how can we optimize yield production, yield potential? So everything starts off with, well, what is the genetic potential of the crop that we're growing? And those crops have to be, viable in the environment that we're growing those crops. With regards to the environment, well, what's crucial is the amount of moisture available to that crop and how warm or cool the season is, and the amount of light and quality of light that the crop can ultimately receive. With regards to soil moisture, well, the amount available to the crop is influenced by the soil texture that the crop will be growing in, and if there's a salinity issue, the salinity limiting how much moisture it can get to that crop. Further, with the soil characteristics, soil texture and soil pH has an impact on nutrient supply potential to that crop. Salinity connected with structure or texture can also create compaction, which would limit root surface area. And really, if we think about it, it's not the nutrients in the soil, it's the rooting characteristics, how much the soil that the crop can explore that determines the nutrient availability to that crop. Now, agriculture science has been researching various aspects of the factors that influence crop growth and crop production. Some of the most influential research may have been done by this individual, Dr. Stan Barber. He hails from Wolseley, Saskatchewan originally, and he did his master's at the University of Saskatchewan back in 1947. And it was the first time that radio-labeled radioactive phosphate was used as a fertilizer in a fertilizer experiment in the world. First time it was done that way. Now, that picture in the top right-hand corner is a picture of a plant, a wheat plant, showing where the radio-labeled phosphate accumulated in that wheat plant. Now, Dr. Barber continued his education, getting his PhD at the University of Missouri, and then had a over 30-year career of research and teaching at Purdue University in Indiana. Now, through those decades of research, Dr. Barber used this technique of radio-labeled nutrients, and what they're able to do was measure the nutrient flux, or the nutrient activity moving through the soil toward and into a plant root, and then ultimately up into that plant. And because they're able to observe the nutrient flux, the nutrient movement, they're able to measure it. And by measuring that under different circumstances, as they did the research, they're able to generate some very sophisticated mathematical models that ultimately could predict the outcome of nutrient activity and yield potential. Now, this was very difficult research work to do, and is even more difficult to apply because of the limitations of conventional soil testing. But that 30 years of research was summed up into a textbook. It's called Soil Nutrient Bioavailability, a Mechanistic Approach. It was first published in 1995 and reprinted in 2017, and it is used as a textbook for graduate level soil fertility classes at our agriculture universities. Now, it is this over 30 years of research that forms the basis of a technology that I've been able to use, had the privilege to use in my 26 year consulting career with farmers. What is that technology? Well, that is PRS technology. Now it has two components. It has the plant root simulator probes and a crop simulation model called the PRS Cropcaster. Let's talk about the PRS probes first. So this was a technology developed at the University of Saskatchewan, and it's an ion exchange resin membrane that's mounted into a plastic holder to form a probe. And when these probes are moved, pushed into the soil, either in the field or in a soil sample at the lab, the resin absorbs the plant available nutrients that the soil is releasing. I have an animated video to share with you, and hopefully that triggers. Looks like it does. So what you'll see here is water being added to the soil. A warm, moist soil becomes biologically and chemically active, and as the nutrients start to cycle off of the clay and off the organic matter, the plant does not care where that nutrient comes from. As long as the nutrients move into the soil solution or the soil water, it's going to be available to the plant. This is a fundamentally different type of soil analysis than the conventional soil test. Conventional soil test grinds up an air-dried soil and applies chemicals to wash the nutrient out of the soil, and then they estimate its availability to a plant. These probes are measuring simply what the soil will supply. In essence, it's measuring only the plant available nutrients, and we like to describe it as a horsepower rating for nutrient supply from your soil. Now, in research, the probes have been used around the world, from the Arctic to the equator, from mountaintop to seashore, and everything in between. And we're officially on all 7 continents with research work that's being done on Antarctica. We had a little bit of challenges, or the scientists did, had some challenges with the penguins because they would see these probes sticking out of the ground and they'd waddle over there and they'd pull them up out of the ground. And the scientists weren't really thrilled with that, so they had to figure out ways to deal with protecting the probes while they're deployed. Now, for farm samples, we collect the soil sample and bring that into the lab, and under standardized conditions of time, temperature, and moisture, the probes are used to analyze the nutrient supply potential of your fields. Now that data goes into the PRS Cropcaster. It's a crop simulation model. And I'm just going to change gears here, bring up the Cropcaster to talk about it for a moment. So to begin with, let's talk about the soil characteristics. Soil density, well, that's if there's any kind of root limitations, roots growing through the soil, because that will ultimately have influence on nutrient supply, or can have influence on nutrient supply to the crop. The water storage index, that is essentially the texture of your soil. And the texture of the soil does also influence how roots grow through the soil, but also the water holding capacity of the soil. So here we're in a Red River Valley, heavy clays. Here would be a clay loam. We're in the loams, and down over here is the sandy soils. After the soil physical characteristics, then we have considerations around the growing season. So we have, for total available water, we have soil moisture, we have the rain and irrigation if it's available. Soil moisture is a measurement we make as we're doing the soil sampling, and to get the amount of stored moisture. And then as if there's additional moisture after sampling or into the spring, well, we can estimate that addition for crop to influence yield potential. Rain is taken from Environment Canada, the nearest weather station, and looking at the 30-year average. And that's the start of the conversation. And we can start at 6, 8, 10 inches of rain. Compare that to 9 or 7. Now for canola, we use maximum temperature during flowering as a yield determining factor. We can have mild conditions during flowering, which is of course optimal, but we know that as we get hotter and hotter growing conditions, that starts having a negative impact on the yield potential. Now for pretty well all the other crops, we use growing degree days as the yield determining factor. Making our way around the loop here, we have soil pH and soil salinity. Well, those are the chemistry aspects of the soil. Those are measured at the lab every time they're requested. And finally, we have the nutrient supply rates here that are generated by the PRS probes. The length, these red bars, consider them to be like fuel gauges. The longer the line, the greater the soil supply rate of that nutrient. And the list of nutrients, this is what, well, we do actually measure more than this, but these are the nutrients that are most applicable to Western Canadian agriculture. Now these fuel gauges, the numbers above the fuel gauges, this is all in farmer speak. This is 24 pounds of soil supply nitrogen, 12 pounds of phosphate, 57 pounds of potassium at 7 inches of rain. Now those supply rates, they do change with the type of growing season that we have. If we have a drier growing season, the soil is less active and there's less nutrient being mineralized from the organic matter and released from the soil complex. If we have a wetter growing season, there's more nutrient cycling and the supply rates go up. Now these supply rates, they also change with the type of crop that we're looking at. So if you think about it, if you pull up a canola plant and you pull up a wheat plant and you take a look at those roots, of course they're different. The rooting characteristics of different crops are built into the crop caster model. And if I'll just get you to kind of watch the fuel gauges here, the supply rates, the nutrient supply rates, and I'm going to rotate between the different crops. And so you can see the differences. So this is what it is for canola. 27 pounds of soil supply nitrogen, 19 pounds of phos, 92 pounds of potassium. This is what it is for corn. It's what it looks like for flax. Here's barley. Back to wheat. I like comparing wheat to oats. For those oat growers in the audience, I just want you to think about this for a moment. When you're fertilizing your oats relative to spring wheat, how do you fertilize your oats? Do you use more nitrogen? Do you use the same or less nitrogen relative to wheat? Now, when I ask that question at trade shows, 95% of the time the farmer answers that they usually dial back on their nitrogen. And that answer is quite consistent. Doesn't matter what part of the prairies that you're growing oats in. But I find that farmers are dialing back for different reasons, depending on where they are. In the drier parts of the prairies, the farmers are dialing back because they just don't see a yield response. And in the black soil zone, so common here in Manitoba, farmers dial back on nitrogen because they have lodging issues in their oats, particularly the older varieties. Now, Grandpa figured that out, and then Dad was doing it, and now we are as we're managing the farm. So we're all dealing with the same symptom, but nobody's talking about the why. Well, let's talk about that now. So where wheat is seeing soil supply nitrogen of 24 pounds per acre, 12 pounds of phosphate, 57 pounds of potassium, I'm just going to switch over to the new oat varieties. 60 pounds of nitrogen, 29 pounds of phos. Here's wheat. Here's oats. Oats has got an incredible root that scavenges the soil far more aggressively than pretty well all the other crops. And so because the crop can find the nutrient that the soil is supplying, we don't have to fertilize that crop as aggressively. So that's what Grandpa had figured out all those years ago, that he could pull back on his nitrogen application on his oats. So just to finish out the different crops, this is what it looks like for peas, very good phosphate scavenger, and this is what it looks like for soybeans. This is, you can see in the fuel gauges here, phosphate and potassium supply rates are very strong. This is why you rarely see a phosphate or potassium response in soybeans, because the soybeans have got a very aggressive root that is, again, exploring the soil far more aggressively than a lot of the other crops. So let's just go back to wheat. Now, I mean, we were trying to grow yield. You may have noticed here with the grain bin that the yield has been going up and down, and we're changing maximum yield. Incidentally, this column of nutrients, this is what you need for the nutrients required to grow maximum yield. Maximum yield here on top of the grain bin for these soil characteristics and for the crop wheat, this growing season scenario. No bugs, no disease, money's no object. Just what's the potential of wheat to grow bushels? And it's an 81 bushel crop. I call that bragging rights on Coffee Row, but not you buying the next round of coffee. What we want to focus on is the yield inside the grain bin. And I'm just going to dial this up to 8 inches of rain, closer to what we have here in Brandon. So we want to focus on the yield inside the grain bin. So we use the farmer's fertilizer costs and what he's expecting for new crop prices. And we focus not on maximum yield, but maximum economic yield, or the most profitable yield. We look at yield response curves for nitrogen, phosphate, potassium, and sulfur. And we try to determine what is the best rate of return on our fertilizer investments. Now, one thing that we need to consider with our bread wheats is that there's a quality that we look for, and then that's the protein content. So looking at the nitrogen curve, the steep part of the curve here, this is where we're building yield. As we go over the shoulder, we start to build protein. Now, where's the protein levels? Well, this spot on the curve is approximately 12.5 protein. This is a 13.5 protein. And going out to the end here, that's a 15% or better. So I've got some examples to share, to compare, and just to start off with the maximum yield here at 8 inches of rain. We've got an 88 bushel yield potential. Let's look at that. Whoops. Just going to have to fire that up again. Go with this one. Fire that up again. And look at wheat at 8. And let's look at some scenarios that I'd saved for you. So this is using initially an 80 cent a pound nitrogen. And I put in a premium for 15% protein. I got these values from a line company here for the third week of January in 2024. So a 15% protein for new crop 2024, they're indicating an 8.22 a bushel for delivery into Brandon. And to grow that 15% wheat, here's the fertilizer blend: 160, 48 pounds of phosphate, 10 pounds of potassium, 9 pounds of sulfur, and we're growing an 88 bushel wheat. That's going to cost us $178 an acre, and we're netting $64. Our break even is $7.49. Now, fertilizing for a 13.5 protein, here's a fertilizer blend. And this is a more of an optimized blend, not going for maximum yield, but maximum economic yield. So we have 120 bushel or 120 pounds of nitrogen, 35 pounds of phos. The potassium curve was pretty flat, so we took that out. There's a little bit of a deficiency in sulfur. So we reduced the fertilizer budget by $50 an acre. We are growing fewer bushels. We're growing 83 bushels instead of 88. But for $50 less risk, we're only giving up $9 in income. So clearly, growing maximum yield isn't necessarily making the best, giving us optimum income. I also compared and did a discount to a 12.5 protein. So to go from a 13.5 protein, so there's the 13.5, down to a 12.5 at about 100 pounds, rounded off there a little bit. The economics on that. So there's here's the 13.5 protein, spending $129 an acre to earn 56. To grow the 12.5 protein with 80 cent a pound nitrogen, we're risking $16 an acre less, but we're giving up $25 in income. So there is motivation to grow for those 3 bushels that we grow. There is motivation to optimize to a 13.5 protein. Now I recalculated that based on a dollar a pound nitrogen, some values that we experienced just a couple of years ago. So here's again for maximum yield, same blend, but now with $1 a pound nitrogen, we're spending $210 an acre to grow that 88 bushel crop. We're only earning $32, $33 an acre. Fertilizing for a 13.5 protein, we're spending, what is this, $57 an acre less. We're only giving up 90 cents. Even though there's 5 bushels difference in yield, we've only given up 90 cents of income for those $50, $57 of risk. And so going down to a 13.5 protein, so there's $20 of risk that we've reduced, gave up 3 bushels of wheat, $20 of risk, we have $21 of income. So this is basically dollar in to get a dollar out. So it's up to your risk tolerance to do that. And then just to kind of close things off, here's what it looks like for canola. Maximum yield at 8 inches of rain, and not much heat stress. There's a 78 bushel maximum yield potential. And if I ask the model to do some calculations, to do a $1.50 return on the last dollar invested, this is the blend that the cropcaster would recommend: a 125, 34, 30 to 32. And we'd be fertilizing for a 68 bushel crop. And because we're not pushing our fertilizer applications out to the far end of the fertilizer curves here, we're optimizing our rate of return. So I can talk about the cropcaster for a long time, but there's some other things that I want to share with you. So I'm going to get back to the PowerPoint. So we've in 26 years of cropcasting and assessing data summaries for over 10 years, almost 15 years. I've been finding some very interesting information, and I'd like to share with you how the weather has been impacting the soil nitrogen supply potential. And the last 4 years have been some of the most interesting years that I've worked with for, I guess, 5 years. So I want to put some regional context to the data. Now, Western Ag, its footprint is in Western Manitoba. So for the majority of the data I'm going to be showing you is from Western Manitoba. And then I have data to share from Saskatchewan, and I'm focusing on the data from Southeast and Northeast Saskatchewan, because that's probably people who have joined in the audience here today. So also I want to talk about the growing seasons to compare how those seasons are impacting the data. On the top row is the May, June, July moisture as measured, recorded, sourced from Agriculture Canada. And the bottom row is the August, September, October rain received. So I'm basically comparing the summer growing season to the fall growing season. So beginning in 2019, we had some pretty good crops. Overall, we weren't too limited in growing our crops here in the eastern Saskatchewan and Westman. But sorry to bring it up, but it's the harvest from hell in 2019. We had 10, 15, 20 inches of rain that we're trying to forget about that harvest. But that moisture helped as we look at the 2020 growing season in the top right-hand corner, that stored moisture helped carry the crop for the following year. And then the dryness continued into the fall of 2020. So it was a very different fall in 2020 relative to 2019. This is what it looked like for 2021, the year of the drought. And for those of you who are farming in 2021, well, now you can empathize with Grandpa, with the drought of 1961, and Dad with the drought of 1988, because they're comparing the drought of 21 to be, in comparison or fairly comparable to those big droughts from Grandpa and Dad. Now, we did get moisture in latter part of August, started accumulating some pretty good amounts of moisture here in 2021. That moisture continued into 2022, and we grew some pretty good crops. But the fall of 22 was really quite dry, and that dryness continued into 2023, dry growing conditions. And then for parts of eastern Saskatchewan and in Manitoba, we did get some moisture starting in August and a little bit more in October. To start recharging the soil for next year. Now, these moisture cycles have had some pretty interesting impacts on nutrient supply potential as we see it at our lab, at the Western Ag Lab. And I'm showing a 5-year data comparison. Now, this is a frequency chart. So how often we're finding basically fields low in nitrogen supply versus fields with medium supply versus fields with high nitrogen supply potential. Incidentally, where we start making recommendations for nitrogen application is anything to the left of the gold circle. Now you'll see the 2019 growing season in the gray bars far left. For that fall, where we had, again, 10, 15, 20 inches or more of rain through that harvest window, we had the snowstorm on Thanksgiving weekend. We had, with all that moisture received, we had leaching, we had denitrification, we had a saturated soil that was cold. There really wasn't any mineralization going on. And so it's no big surprise that we see a lot of fields that are low in nitrogen supply potential. And the Western Ag analysis was very similar to what the conventional soil test was seeing. There's little nitrogen in the soil. Now in the fall of 2020, again, it was a very different fall compared to the fall of 2019. And our analysis started seeing nitrogen supply potentials spiking, which is really quite unusual. But we saw that, but because Western Ag customers could see nitrogen supply potentials for some of the fields about approaching 30% or about 30% of fields, they could really dial back on their nitrogen applications, planning for the 2021 crop year. Now, no one knew that the drought was coming, but because the Western Ag customers were not applying as much nitrogen, after the drought, there wasn't as much unused nitrogen, residual nitrogen in the soil. So we had a little bit of a drop in nitrogen supply potentials relative to 2020. Now, to be fair, Western Manitoba did not have the same degree of drought as many other parts of the prairies. So there was more nutrient uptake and utilization by the crop as well. Now, in the fall of 22, we had the dry fall, and then now this recent year, we had the dry conditions, 2023, with some moisture in August and October. We're seeing even higher nitrogen supply potentials. So in Manitoba, altogether is 64% of fields that we sampled are low in nitrogen and need supplement. But to say it another way, 36% of fields need very little additional nitrogen to grow the crop. Now, to compare, if there's anybody from Northeast Saskatchewan, and I guess when I say Northeast, this is basically north of the Qu'Appelle Valley, and we see a kind of a similar pattern. We have the 2019, the very wet fall, drawing down or having a lot more fields that were low in nitrogen supply potential. 2020 for the Northeast was maybe a little bit more of a closer to a typical year, but we were seeing a little bit of nitrogen spiking. Then the drought of 21 just hit the Northeast of Saskatchewan. Like they haven't seen a drought like that since 1988. Then we had the dry fall of 2022 and the conditions of 2023. Same kind of pattern as we saw in Manitoba. This is what I saw in Southeast Saskatchewan. Again, 2019, the very wet fall, drawing down nitrogen supply potentials. And we had, if we look at on the hard right here, dry fall of 2020, drought to 21, dry fall of 22, dry conditions with rain in August in 23. And we saw, well, for the fall of 2023, 40% of fields have require very little additional nitrogen to achieve yield potentials. Now, what is happening in the soil? Well, when soils go through an extended period of drying, there's physical and biological changes that happen in the soil. In the scientific literature, it's described as what this can, I guess, these drying conditions can result in is a mineralization burst. So they sometimes call it a drought-induced nitrogen mineralization burst. They're nicknaming it the Birch effect by a fellow who started to first write about it back in the 1950s. I like saying Birch effect because it's a little handier handle to describe what's going on. But if we look at this graph, and I'm just going to zoom in on that a little bit more, along the bottom right-hand side, you see the weeks of drying before rain arrives. And then on the left-hand side, you have your soil organic carbon content. If you multiply by 1.7, it's approximating what the organic matter content of the soil is. So the birch effect, this mineralization burst when there's dry conditions, like I feel that this happens in the Western prairies almost every year, because Southwest Saskatchewan, it's always dry there. So if you think of nitrogen mineralization like a rubber band, where every week of dry, you're putting a wrap on the rubber band, and the more weeks of dry, you're putting more and more potential into that rubber band. And all you need is a warm soil and moisture, and that release will happen. Now, again, I mentioned Southwest Saskatchewan. I think this is happening often, but because they don't have a lot of organic matter in the soil, it's like putting wraps on a skinny rubber band. And so when they do get rain, there really isn't that much of a nitrogen burst that happens. But if you transition into the dark brown and into the black soil zones, black soils here in Manitoba, it's like having a heavier and heavier rubber band. And as you put the wraps on that rubber band, 3, 6, 12 weeks of dry conditions, there can be an awful lot of potential that builds. Now that potential is released with a warm soil and moisture. And what we had in 2020, we went into freeze up dry. And that dry fall, when that mineralization potential remained until the following spring. And this is where we differed from conventional soil testing, where we could see a mineralization potential building. A conventional soil test was not seeing this nitrogen. Because, well, a conventional soil test is measuring nitrate only. And to compare 2019, the year of with all that rain that we had through the fall, versus the fall of 2020, where we had a drought for 3 months, the conventional soil tests were seeing nitrogen supply, nitrate supply being very similar. And I thought that was very puzzling until I realized that it is all related to moisture. In the fall of 2020, there's so little moisture in the soil that there's no biological activity. With no biological activity, there is no nitrogen mineralization. With no mineralization, there's no nitrate to measure. So the conventional soil test was correct in that there was no nitrate to measure, but they were not accounting for this mineralization potential that was building. Now, Western Ag, I guess to talk about, well, how different ways that we can see this, or some of the research. This is a more recent a paper published in 2022, and it was using actually work done in Switzerland using perennial ryegrass, and they induced drought on plots, and they did this by using rainout shelters, basically shedding the water off but letting the light in to let the perennial ryegrass grow. The shelters were in place for 2 months, then they removed the shelters and irrigated the trial site to get everything up to the same conditions, moisture conditions. Then they had extra treatment of with and without fertilizer. Now with fertilizer, like, it was hardly anything at all. That works out to about 12 pounds an acre. And but it was quite remarkable that when the PRS probes were inserted, the nitrogen supply over 27 days, that we could see this nitrogen mineralization burst. We could see the birch effect happening. Now, this isn't an artifact. The researchers continued the trial to collect dry matter yield, and you can see the yield coming off those plots mirrors what the nitrogen supply measured by the PRS probes. So again, this isn't an artifact that the PRS probes is measuring. It is nitrogen that is available to the plant. So when we have very dry conditions in the soil coming into the lab, we do an extra procedure. We measure everything for moisture content, and if it's below a certain threshold, then we do what we call a pre-wetting protocol. And I'm going to show you what that impact is in the cropcaster, the crop simulation model. So using our standard protocol where we collect soil, bring it into the lab, moisten it to field capacity, insert the probes for 24 hours, remove and analyze. We have our standard protocol, and we see nitrogen supply potential of 22 pounds per acre. If we do a pre-wetting protocol where we, under controlled conditions, we trigger the birch effect in the lab, we see, in this case, 4 times the nitrogen supply potential. 4 times. and so up to 85 pounds of nitrogen. And so in this case, the farmer was able to reduce his nitrogen application by 60 pounds per acre. It's a big impact on the economics, and also the nitrogen isn't in the environment. Now here's an example from a farmer from north of Saskatoon. So he's well into the black soil zone up there. This soil sample was collected in the fall of 21 following the drought. Now this is an aggressive farmer. He likes to fertilize pretty hard. But when we take a look at that nitrogen fuel gauge, and I have it circled there, our analysis was showing 210 pounds of soil supply nitrogen available to the wheat. Now there will be residual nitrogen here, absolutely, but there's also birch effect nitrogen in that measurement. So my colleagues were telling this farmer, you don't need any nitrogen, just need some phosphate, 30 or 40 pounds, but there's sufficient nitrogen to grow that 89 bushel crop. Now, if you look at the picture, some farmer psychology came into effect here, and you'll see that there's a highway and there's a town. And so as a farmer with a field along the highway and close to town, is he not going to put any fertilizer on that field? Well, he succumbed to those pressures. And so he did just-in-case management. So the farmer applied 80 pounds of nitrogen, 30 pounds of phosphate as a blend. Now my colleagues were able to convince the farmer to reduce his nitrogen, or to reduce his fertilizer on a couple of strips. But he was begrudgingly, he only did 2 strips of zero fertilizer. Now, it isn't really fair. We were asking for phosphate, but logistics didn't allow that experiment. So we compared a couple of strips of zero fertilizer to fertilized in the rest of the field. So after harvest, they went back to the farmer, and with the John Deere equipment that he runs, he's got all the high-end data management, and they're able to gather the yield information for 5 strips before and 5 strips after the 2 unfertilized strips. And this is what it looked like. You will notice that in every instance, the fertilized crop yielded less than the zero fertilized treatment. And in this case, for using $1 a pound nitrogen and $10 wheat, the farmer's net income reduced by $160 an acre. His net income by $160 an acre. And what was going on? Well, we had the 210 pounds of soil supply nitrogen that we were predicting. The farmer added another 80 pounds, so there's 290 pounds total being made available to the crop. An 89 bushel wheat crop, it only demands about 190 pounds of nitrogen. So if you think about it, the farmer was 100 pounds beyond the maximum demand for 15% wheat. 100 pounds onto the backside of the nitrogen response curve. And it cost him $160 an acre. So our federal government has got aspirations to reduce greenhouse gas emissions, particularly for agriculture, to reduce our nitrous oxide emissions. And industry and academia, are promoting the program to help us in that effort. It's a 4R nutrient stewardship program, and that's where we apply fertilizers by the right source, the right rate, the right time, and the right place. From my perspective, for all these considerations, what we need to be focusing on first is the right rate. So to summarize, successful, sustainable farming requires a focus on profitable return on investment. Understanding the constraints to yield potential will help you optimize your fertilizer investments. PRS technology measures bioavailable nutrient supply, focuses on maximum economic yield, and tailors plans to your farm. And weather cycles have an impact on soil nutrient supply potential. Understanding that potential improves our efforts in stewardship and in profitability. And with that, I welcome any questions and discussion.